Okay, let's continue the discussion about polynomial functions. Uh, in the first part, we already discussed the power function, x twin, f x equal to x twin. And in this discussion, you have two cases. One, n is even. The other one, n is odd. Even for the even power, x twin is the even function. For the odd power, x twin is an odd function. Okay, and you have the graphs. Second, let's graph certain simple polynomial functions. Using transformation. For example, if we want to graph fx equal to 1 minus x to 5, how do we graph this? Okay, we are going to do in 2 steps. Step 1, I think we are going to do in 3 steps. Step 1, we are going to graph x to 5. X to 5, this is an odd power, so it's an odd function. Odd function, the graph must pass through 1, 1, 0, 0, negative 1, negative 1. So it's like this. This is a x equal to 5. X to 5th power. And then we're going to flip it. Flip it about the x-axis. If you flip it about x-axis, you will get the coefficient negative 1. Okay, when you flip it, you see here, this point is flipped to 1, negative 1. This point is flipped to negative 1, 1. And 0, 0 is still 0, 0. Oops. Oh, let's shift it a little bit. So this is the graph x equal to, the graph negative x to 5. Okay, so this one, reflection. Reflection means you multiply it by negative 1. And then we're going to shift, because this one, you see here, it's equal to negative x to 5 plus 1. After you get this function, you're going to shift it up 1 unit. So every point is shifted up 1 unit. 0, 0 is shifted here. Negative 1, 1 is shifted here. And 1, negative 1 is shifted to the x-axis. So x to 5 plus 1, or 1 minus x to 5, fx. Okay, so that's our first example. We first get the standard power function, and by reflection we flip it up and down but because of this negative sign, and then plus 1 you shift it up 1 unit. Okay, it's the first example. Okay, let's see second one. We're going to do examples and try to demonstrate. We're going to sketch the graph of fx equal to 1/2 x minus 1. What's this? To 4th power. Okay, to 4th power. Okay. You have 2 ways to do that. In order to get this, you see here, the basic function is x to 4. X to 4. You can first multiply it by 1/2, the vertical compression, and then subtract 1. It's a horizontal transformation. Or you can do the horizontal transformation first and then vertical compression second. In the textbook, they do the horizontal transformation first and the vertical compression second. In this note, let's try the other way, okay? Okay, so this is x to 4. X to 4 is even power, so it's an even function. Even function. The graph is symmetric about the y-axis, so. This is assumed to be the graph of x to 4. It's 1, 1, negative 1. Okay, then let's multiply it by 1/2. This coefficient is 1/2. It's a vertical compression. Okay, so when you have 1 and negative 1, the original value is both 1, but by this 1/2 it becomes 1/2, and 0 is still 0. So it's flattened out. It flattened out, right? It's more flat. You compress it to the x-axis. Okay? And then you're going to construct the graph of function x minus 1 to 4th power. Minus 1 move to the right. Okay? So 0 is moved to 1. 1 is moved to 2. Negative 1 is moved to 0. Everything is moved to the right. Okay? And at 0 it's still 0. This is just a horizontal shift. At 1 it's 1/2. So assume this is 1. This is 1/2. At negative 1 it's also 1/2. Okay? So you can compare this result with a graph in the textbook. They are exactly the same thing. So here you can do the selection either horizontal transformation first or vertical transformation second, or the other way. Okay. Okay. So those are two examples about graphing functions using transformations. First of all, this method cannot give you the graph of all possible polynomial functions. They just give you the graph of certain functions which you can do graph by transformations. Okay, they are special tricks. It's not a universal trick for everyone. No. Okay, it's just a technique, a method. And now let's see the next part. This is a section, not section. This is a second part. The third part is to identify real zeros of a polynomial functions and their multiplicities. So identify the real zeros of a polynomial function and their multiplicity. And their multiplicity. Okay, so to get the real zeros, so what is a real zero? First, let's see the definition. If f is a function and r is a real number, for which fr is equal to 0, then r is called a real zero of f. Okay, the value which make the function 0, the input which make the function 0 value is called a real zero. The input, real zero, is the input. Because of this, you see here, it's a solution, it's a X-intercept. Because of this definition, we have 4 equivalent statements. 1, R is a real zero of a polynomial function. Okay. Second, R is an X-intercept of the graph of F. Because you see, what is the intercept? Intercept means when you let y be 0, you look for the x. So R is x. So that's why it is a X-intercept. 3, x minus R is a factor of F. We're talking about polynomial function. When we only talk about polynomial function, when x minus R is a factor, it makes this whole polynomial function 0. Okay. 4, R is a solution to the equation fx equal to 0. So R is a solution, R is a real 0. They just mean exactly the same thing. Okay. So you will see that 0 solutions, intercept, factors, they are basically represent exactly the same concept. Okay, let's see examples. When we have a polynomial, well, we try to construct, we try to find its solutions, or we try to find its real zeros. But sometimes we just point out several points, say, okay, we fix those points. We're going to find a polynomial function so that those points are the solutions. So find a polynomial function of degree 3 whose zeros are -3, 2, and 5. Okay. Let's check. We're looking for the polynomial. When you have, for example, when you have a 0, 2, R is 2. R equal 2 is a 0, is a real 0. Then by these 4 equivalent statement, we can see that x minus 2 is a factor. Then x minus 2 is a factor of f. Okay, so you have a factor of f. And similarly, x minus 5 and x minus -3 are factors of f. Okay, so this f has 1 factor, 2 factor, 3 factors. Then the product of those 3 factors are also a factor of f. Then x minus 2, x minus 5, x minus -3 is x plus 3, is a factor of f, a factor of f. Okay. And another thing, this is degree 1, degree 1, degree 1, but after you multiply it out, you will have degree 3 because you have degree 1, degree 3, degree 1, degree 1, degree 1. The product, you add the degrees. So this is already a degree 3 polynomial if you multiply it out. And in our problem, we require f to have degree 3. So f cannot have additional factor. If f has other factor, the degree will exceed 3. Okay? F has degree 3. So fx is this product almost with a coefficient a, with some coefficient which you have no idea, because in the problem they only give you the zeros, they don't give you the information to determine the coefficient. A is a real number and a is not 0. If a is 0, the product is 0, it's useless. It's not interesting, and also the degree violates the condition. Okay? Okay, so this is like a construction. If you have 3 solutions, then the polynomial of degree 3 is almost determined except the leading coefficient, It can be selected to be any non-zero number. Okay? B is used to graph it. We are not going to do it because it's we will discuss that later, and we cannot use calculator, so we do not discuss the B part. Okay, so that's a 0. You have a 0, you have a factor, you will have a 0. Okay? Okay. Second, for example, if we have fx equal to x minus 1 squared, it is x minus 1 times x minus 1. Even though we can only say x equal to 1 is a real 0. But this 1 actually appears twice. It appears twice. So we want to present this the times. So we have the following definition. If x minus r to m is a factor of a polynomial, f, and x minus r to m plus 1, if you increase the power, this is not a factor of f, then r is called a 0 of multiplicity m of f. So basically we want to also record the how many times this real zeros appears. Okay, we call this this quantity by the multiplicity. It's called multiplicity. Okay. For example, if we have a completely factored polynomial 5x minus 2 x plus 3 squared x minus 1/2 to 4th power, then we will see that 2 is a 0 of multiplicity 1. There's no power, means the power is 1. X plus 3, the real 0 is negative 3. It's x minus negative 3. So negative 3 is a 0 of multiplicity here 2. And 1/2 is a 0 of multiplicity 4. We just read the power from the corresponding factor. Okay. Okay. So next, let's try to graph a polynomial using the X-intercept. Assume we have a completely factored polynomial. Completely factored polynomial. Then we first find x and y intercept. Y-intercept, this one is simple. Y-intercept is f of 0. Y-intercept is always f of 0. F of 0, check here. When x is 0, is 0. So y-intercept is x0, is 0. X-intercept is a solution of fx equal to 0. The solution of fx equal to 0. Fx equal to 0, either x is 0 or x minus 2 is 0. X minus 2 equal to 0, x is 2. So you get either x is 0 or x is 2. Okay, so this is an intercept. The second one, use the X-intercept to find the interval on which the graph of f is above the x-axis and the interval of the interval on which the graph of f is below the x-axis. Okay, how do we do it? So we want to use x-intercept to find where the graph is above x-axis and where the graph is below the x-axis. X-intercept 0, 2. First of all, on those 2 points, the graph is just 0. This is a graph. Actually, this point belong to the graph. And those 2 points, you have 2 points, you have 3 intervals, left, middle, right. If you have a 3 point, you will have 4 intervals. Okay, the number of intervals is bigger than the number of the x-intercepts by 1, greater than it by 1. So you have 3 intervals. Now, from each interval, you are going to pick up some sample point. So for example, in the left interval, whatever number you want, but you should select the number so that you can easily evaluate. You will not choose 0.1234. That's too difficult for us to evaluate. Okay, so here I possibly will select the -1. I select the -1. I'm going to evaluate fx at -1. Okay, so -1 squared and 1 minus -1 minus 2. -1 squared is 1. -1 minus 2 is -3. So this value is negative. Negative means it's always below the x-axis. So this part is below the x-axis. Okay, so the whole interval, over the whole interval, the graph is going to be below the x-axis. And between 0 and 2, I possibly will select the 1. It is easy to compute. We'll get 1. Let's see f1. f1 is 1 squared, 1 minus 2. 1 squared is 1, 1 minus 2 is negative 1. So it's still below the x-axis. Okay? And when it is greater than 2, so this part, this one is below. When it is greater than 2, let's select a 3. Then f of 3 is a 3 squared, 3 minus 2. 3 squared is 9. 3 minus 2 is 1. 9 times 1 is 9. Okay, so it's above x-axis. Right? So by this evaluation, you can clearly list them by the following. Here is like a scratch, and then you can formally write f of negative 1 is negative 3, f of 1 is negative 1, and f of 3 is 9. With those evaluations, you can say on the intervals negative 1 is from the left interval, negative infinity is 0, and on the middle interval 0 and 2, don't include 0, because at 0 is equal to 0. Okay, it's not above, not below. On those two open intervals, the graph is, you see here, below the x-axis. On the right interval, the graph is above the x-axis. It's above the x-axis. Okay. So that's our idea. We choose a sample point from each intervals, and you will always select the sample point so that you can easily evaluate. You will never make yourself in trouble, right? Okay. So that's the property. And from this part, if we can sketch, if we have enough sample point, we can sketch it. If you sketch it, so far we cannot, because we didn't do a lot of test or computation. But if you can do that, it looks like this, the graph. Okay. The graph is more or less like this. Okay, so here is below the x-axis, here is below the x-axis, and then it's above x-axis. And this graph also give is an example for the next observation. The next, not observation, suggestion or the conclusion. The next conclusion says here, this 1, this 0. This 0 comes from the factor x squared. So the multiplicity of 0 is 2. Multiplicity of 0. 0 has multiplicity 2. It's an even number. We understand it as an even number. If it's an even number, the graph touches the x-axis. Okay, it touches x-axis. And this number 2 has multiplicity 1. 2 has multiplicity 1. We consider it as odd. It's odd number. The graph crosses the x-axis. Okay, so this is like the supporting evidence for the claim. The claim is the following, the same thing. If R is a 0 of even multiplicity, like 2, 4, 6, 2, 4, 6, it's even multiplicity. Then we have two conclusions. First, the sum of fx does not change from one side to the other side. Of R. R means this R here, R. This is 0. So what does this mean? This just means when you have an even multiplicity zeros, the left side is below the x-axis, right side is also below x-axis. Or if it's above it, the left side is above x-axis, then the right side also above the x-axis. Okay? So to keep the sign, this is negative, this is also negative. Below the x-axis is negative, above x-axis is positive. The value is positive. Okay? So you don't change the sign. And this is about the sign, the algebra. The geometry is that the graph of fx touches the x-axis. Okay, the graph will touch its x-axis. That's an even case. If R is a 0 of odd multiplicity, if you have an odd multiplicity, then first the sign of fx changes from one side to the other side. Of R. So you see here, on the left side the sign is negative, on the right side the sign is positive. Okay? Below the x-axis it's negative, above x-axis it's positive. So that's what it says. If you have an odd multiplicity, then definitely on two sides of this 0, one is positive, the other one will be negative. And oops, so this is 1, 2. The second thing is that the graph crosses the x-axis. The graph of f crosses the x-axis. Okay, so you just understand this this property based on this example. Okay. After we after we got this property, why the shape is like this? Why is the shape of the graph like this? So we have another conclusion. The behavior near a 0. The behavior near 0. We still use this example. Okay, so let's talk about the 0x. X equal to 0. When x is near 0, this is the first 0. This one, the first 0. When x is near 0, x is close to 0, then x minus 2 is near negative 2. 0 minus 2 is negative 2. X minus 2 is near negative 2. So fx is close to, okay, this is negative 2. We replace x minus 2 by negative 2, close to negative 2 x squared. X squared term you don't change. Only change the thing which is not have 0 in this at this point. Okay, so we're talking about a 0. 0 comes from x squared term. So you keep x squared term and you estimate other terms. Okay, you will always keep the the term which give you these solutions and estimate others. Okay, so fx is close to the polynomial negative 2x squared. What is negative 2x squared? What is the graph? The graph is like this. So when your x is close to 0, the graph, I'm talking about this graph in this area is close to the original graph. So these two graphs will be very similar to each other. So that's why we sketch the graph based on the like the even power function. Okay, and when x is near 2, when x is near to 2 is the second solution. When x is near 2, then x squared is close to what? 2 squared is 4. X is near 2, you use 2 instead of x, you get 4. So the function fx is close to 4x minus 2. Again, you see here, you're talking about this 2, so you keep this factor x minus 2 and estimate the other factor. So it's a linear function. Linear function, you see, this is a linear function, the graph of linear function. So that's why when it is very close to the point, this segment, the part of the graph will be very close to the straight segment like this. And straight segment, of course, cross axis. And this part, the polynomial function, it does not cross axis. Okay, this is even power function. So that is the behavior near a 0. So let's summarize a few things, 2 things. One, the multiplicity of a real 0 determines whether the graph crosses or touches the x-axis at 0. At the solution. So the even multiplicity touches x-axis. Odd multiplicity cross x-axis. The behavior of the graph near a real 0 determines how the graph touches or crosses the x-axis. Okay, so this part, you see, when it is near 0, it touches x-axis like the negative 2x squared. When it is close to 2, it crosses x-axis like 4 times x minus 2. So that's what it means. Okay. Okay. Another thing, we just try to understand how we sketch the graph. We have this one, and I just simply sketch it like this. What happened? I mean, can we do something like this? And close to it, it's a negative 2x squared. It's fine. And can we do this shape like this? Can we have a lot of wave in a way? Okay. Can we have a lot of up and down case between the two zeros. You see here, it's still the same thing. The left part, this part is below x-axis. Here is below x-axis, and here is above x-axis. But between them, can we have a lot of waves? And to discuss the waves, we need the turning point. Okay, the turning point. The points on the graph at which the graph changes direction are called turning point. Turning points. So for example, this point is a turning point. Why it's called a turning point? On the left side, it's going down. The direction is going down. On the right side, it's going up. It's going up. So direction. This is direction. You see, here the similar direction. On the left side, it's a similar direction. It's always going down, and here it's going up, and this is called a turning point. Okay. So if you have a lot of wave, you will have a lot of turning point. Even though the wave is below x-axis, they are always turning. This is turning point. This is turning point. This is turning point. Turning point. Turning point. There's many turning points. So our question is that, can we sketch the graph like this? If we can do that, then we will have a lot of turning point. Okay. Now let's check. There is a theorem which we cannot prove. It's called the turning point theorem. The turning points theorem says if f is a polynomial function of degree n, is a polynomial function of degree n, okay, then the graph of f has at most n minus 1 turning points. Okay, so you don't have a lot if you have a polynomial function. You don't have a lot of turning point. Okay, so if your degree is fixed, then your turning point has a roof at most n minus 1. And equivalently, if your turning point has a fixed number, if the graph of a polynomial function f has n minus 1 turning point, then the degree of f is at least n. So it's the floor. The floor is n because the turning point is already n minus 1. Okay, so let's check. For this function, remember x squared x minus 2. Close to 0, it looks like negative 2x. It is very close, negative 2x squared. Close to 2, it's close to 4x minus 2. So you get something like this. This is the graph 4 times x minus 2. This is a graph of negative 2x squared. Okay, so here this point is already one turning point. It's already one turning point. And this part is going down, this part is going up. If you want to connect it, if you want to connect those two graphs, definitely there is one turning point. Definitely you have to go from down to up. So you have one turning point. And this is a polynomial of degree 3. This is a degree 3 polynomial. So you already have two turning points. That's a maximum possibility for a degree 3 polynomial. So except those 2 points, there's no other turning point. Okay? So because you have to have two turning points already. So any other point you cannot have a wave. If you have a wave, you will generate additional turning point. Then it will violate the degree 3 condition. So the graph has to be like this. And also here it just goes straight up. Okay. Next, let's check. Assume we have several curves like this. Whatever, I just sketch it. This is solid, and this is a circle, and it goes this way. If you have a curve like this, then this curve cannot be the graph of a polynomial function. It cannot be the graph of any polynomial function. The reason is that the curve is not continuous. Because it is not connected. The graph has to be connected. It has a jump. Okay, so the first case. And second, this is -2, +1, and +2, and -1, -2. This bottom point is -2. Okay, if you have a graph like this, then this could be the graph of a polynomial function. Well, it's reasonable. You have -2, you have 1, you have 2, so you have 3 solutions. For example, you have x minus 2, x minus 1. When I have a 0, you get a factor, and x minus -2. Okay, and this is this product satisfies those 3 zeros. And next, we want to determine this the y-intercept -1. How do we get a y-intercept equal to -1? You put a coefficient here, and you call this fx. Then let's determine this leading coefficient. So f0, y-intercept f0. f0 is equal to a times 0 minus 2, -2. 0 minus 1, -1. 0 minus -2 is +2. Okay, so it's a 4a is equal to -1, so a is a -1/4. That's good. So the polynomial function could be -1/4, x minus 2, x minus 1, x plus 2. This is a possible graph. Okay, and if we have C it's like this, whatever horizontal graph. C, if you have a curve like this, then this curve cannot be the graph of a polynomial function. It cannot because it has a corner. The graph has, the curve has a corner. The graph of a polynomial function is a smooth graph, so it cannot allow corner or cusp. This one, it just violates that corner condition. And for you have a this is -2, this is +1. And this graph, it's smooth, it's connected, so it could be, this could be the graph of a polynomial function. But this one is more complex than the second case. Second case, you see here, you have 3 zeros. Then the simplest function will be the product of those 3 factors and with the coefficient. And it has 2 turning points, so this is degree 3, the maximum turning point is 2. Everything is perfect. But here, you have 2 zeros. You have 2 zeros, if you just put x minus -2 times x minus 1, and this is not enough because this only has degree 2. This has degree 2, then its turning point can only be 1. You can only have 1 turning point because here have degree 2. But this place, you see, you have 1 turning point, 2 turning point, 3 turning point. So it implies if it is a graph of a polynomial function, then this polynomial function has to have degree 4 at least, degree 4 at least, because you have a 3 turning point, 1, 2, 3. 3 turning point, the degree of a polynomial is at least 4. So you will have some ax squared plus bx plus c, some quadratic polynomial here. Then you have degree 4, and we are not going to determine what this is, but you have to realize the degree is at least 4. Okay, so this is one of a different point. Okay, so let me see. This is a very long section. Let's. I used to explain because of my cell phone's some characteristics. I can only take a video up to like 55 minutes. So here is already 54 minutes. Let's stop this video and continue the second video to complete this section. Okay? Okay. I'm going to stop this video and start another video.